So we have seen in the previous lecture how we can introduce damage mechanics to simulate fracture in a smeared way. What problems you have and how you can extend it, how you can repair these problems by resorting to non-local approaches or gradient approaches. One of the other approaches which is often used in rocks and soils is the Costra approach. And I alluded to that already a few times when I said you can also drop the assumption that when you go smaller and smaller that you arrive at a homogeneous stress distribution, but instead have a linear varying stress distribution, which is statically, of course, equivalent with the normal force and the bending moment. That idea was conceived more than a century ago, in 1903 to be precise, by the brothers Costra, and was, I think, the first enriched continuum model. You can, and I will show that now, also combine that with things like plasticity. And I will give you some examples of how you're doing that. Now, what are the kinematics of such a model? Well, normally you are used to the fact that you define your shear strain as half dux dy plus half dy dx, and that you define epsilon yx identical to epsilon xy. Your strain tensor is symmetric. This does not have to be the case. You can define the rotation of a microscopic element by an independent rotation. For instance, when you think of any granular material where the particles are relatively rigid compared to the total stiffness of the medium, where deformation is caused by, for instance, rolling of particle or displacement of particles rather than by deformation of the particles itself, then rotations of the particles are important. They can roll over each other rather than purely deform. And in that sense, including the rotation of the particles, even in an average sense, over small volume makes sense. So what we here have is we define now our epsilon xy as dux dy plus the rotation around the z-axis. So we have x, y, z. We have a rotation around the z-axis as an independent kinematic variable in addition to ux and uy. So we have three independent kinematic variables. So here we define epsilon yx as duy dx minus omega z. Of course, if you add them, epsilon xy plus epsilon yx, then the rotation falls out and the total shear strain, total amount how this angle becomes smaller, still remains dux dy plus duy dx as it is in our classical continuum. Now, since we have a rotation this kinematic degree, we also have curvatures, microcurvatures, which are possible. So for this elementary particle, we of course have the strain, the axial strain in x direction and in y direction. They are not affected, they are as before. We have our shear strains, a different one, epsilon yx from an epsilon xy. But also, we now have our rotation, which can cause a curvature. So we consider this as a sort of mini beam, micro beam, which you can do like this. And also like this. So we can do it in both this direction and in this direction. So this microcurvature is kappa zx. It's the derivative of the omega z dx. And similar, we have in the direction orthogonal to that, kappa zy is the derivative of the rotation, the additional degree of freedom, with respect to y. And it's the simplest possible extension of a standard continuum mechanics theory. Now there is a special case which you sometimes have as constraint Costra theory, and then if you define omega z as a half times this minus this, then you would retrieve what you classically have. Indeed, substitute this expression into here. Then you get dux dy plus half dy dx minus half dux dy is half dux dy plus half dy dx. Same when you substitute it here, you get dy dx minus half dy dx minus minus, so plus half dux dy. So in that case, when you have this rotation as this, as a traditional implied rotation which you would have, then you get back the classical kinematics. Now, if you have additional kinematics, you also need additional stresses, additional statics. So you need stress measures that are conjugate to these additional strain measures. So, of course, we have our normal strain, nothing changes, our normal stress is their conjugate. We have our shear strains, also there our shear stresses are conjugate, but already there's one thing. We have different shear strains, they can have different values. So sigma xy, which is conjugate to epsilon xy, can be different from sigma yx, which is conjugate to epsilon yx. So we have, in that case, a non-symmetric stress tensor. Normally you would think non-symmetric stress tensors only appear for large strains. Here you have non-symmetric stress tensors already for small strains. In addition, you have stress measures that are conjugate to these microcurvatures. And these are little bending moments. And they have been drawn here. So here are the normal stresses, sigma xx, sigma xy. But also we have a moment m xz, the moment on x-plane directing in the z direction, because it's around the z-axis, which is a moment which is causing this kind of curvature, this kind of bending. Similar here, in addition to the normal stress and the shear stress, we have a bending moment, and here, which causes something like a bending, a little curvature there. Now, these effects already play in the elastic regime. So, what we do here is we have now, we simplify for the moment to 2D configurations. We don't go to 3D, which makes it would make it a bit complicated. So as independent strains, we now have epsilon xx, epsilon yy, and for the plane strain case we would also have epsilon zz, epsilon xy, epsilon yx, plus our microcurvatures. And here I've multiplied them with an L, parameter with the dimension of length, in order to make them dimensionless, to have them, give them the same dimension as the normal strains and shear strains, because the curvatures are of dimension 1 over L. Multiply them with L, and they are again dimensionless. Essentially, this L is the size of the smallest volume over which we can homogenize. In classical continuum, we assume that we can homogenize up to a point. That's physically not always possible. So in some cases, you have to say, okay, there's a lower limit, and this length is set by this parameter L. Similarly, the conjugate stresses, the normal stresses, the shear stresses, and our micro bending moments, which are again now divided by L in order to make them of the same measure as this. This is Newton per square millimeter. The bending moments are of course Newton per millimeter. Therefore you have to divide them by an additional length in order to have them of the same length, dimensions. Now, if you go to the balance of momentum, of course, longitudinal balance of momentum is not a problem. But when you look into the balance of momentum, then you get a different term. Normally, you have sigma xx equals sigma xy. Sigma xy equals sigma yx. Now you have these bending moments in addition. So when you take rotational equilibrium, you have this times this lever arm, minus this times this lever arm, plus this bending moment, minus this bending moment. Or plus this bending moment. So here you get that the derivative of the bending moment of this one in the x direction, plus this one in the y direction, minus this shear stress, plus the other shear stress, equals 0. And here you see that you have a non-symmetry indeed of your stress tensor. Also here you see it, because normally this term will not be 0. The bending moments are not 0. So you see that you have no symmetry anymore of your Cauchy stress tensor, and you get an introduction of your internal length scale, of an internal length scale. Now, We have had the kinematics, we have had the statics. We still need some constitutive relation. Well, the simplest possible case, that is of isotropy for 2D situations, is this. So here you still have your normal shear modulus. Here you have your normal expressions C1 and C2, which depend on your Poisson ratio. So this is for plane strain conditions. Here you get additional terms. So when you look into your relation between your shear stresses and your shear strains, you have an additional modulus, mu c. And this is the relation, the shear relation here. So in total, you get two additional material parameters, mu c, mu c, and L. And mu c has a normal, is the same dimension as the normal shear modulus, but L has the dimension of length, and therefore introduces an internal length scale, and therefore you can have size effects in such a continuum. And also, when you do numerical calculations with softening, for instance, then you get mesh-independent solutions as a consequence of this. Now you can extend this also to plasticity. So you do the usual thing. You separate the strain into an elastic part and the plastic part. You take, for instance, a Drucker-Prager yield function, which is something like, here you have the J2 invariant, here you have a friction coefficient, your pressure, and here you have a yield strength. Obviously, you have the von Mises yield function as a special case when alpha equals 0. But what you have to do is you have to enrich the expression for the second invariant. You have to include now not only the deviatoric stresses, but also the bending moments. And again, in order to make them of the same dimension as the normal stresses, you have to divide them each by this length L. So normally you would have half here and half here. Now this is only a constraint. So your choice becomes much wider. So in matrix notation, you here have just the normal ones. Here you have additional terms, and this is related to the bending moments. So you have now in a matrix vector notation your yield function as this, sigma times this matrix times this, plus alpha times the projection vector of the stresses minus your yield function. Now in plasticity you not only have yield functions, but you also have plastic potential functions. And for metals there is normally no difference. For geomaterials, but also for ceramics, there is a difference. These materials are pressure dependent, and in that case the flow rule, the expression for the plastic strain rate equals a multiplier times the derivative of this plastic potential, rather than the yield function. So we have typically a plastic potential that's very much similar to the yield function, but with a dilatancy factor rather than a friction factor. So if we substitute this in here, we can get this by simple differentiation. And again, we have to define a different expression for our hardening parameter. Normally, we have just 2/3 times this, or 1/3 times this, plus another third times this, which doesn't matter because epsilon ij is symmetric. But now we have also to add the plastic microcurvature rates. And again, you can put that in a matrix vector form, which is convenient, and you can go back in the end to a classical scheme for elastoplasticity, except for the fact that you've extended the vectors for the stresses and the strains with two entities, namely the microcurvatures and the bending moments. Plus, you have to make distinction between the epsilon yx and epsilon xy, and a sigma xy and a sigma yx. Now, you can then write that your new stress is equal to your old stress plus an elastic part minus a plastic part. You can write this plastic part as such. You substitute this into here to obtain this, and you can finally solve for this unknown amount of plastic flow. This is a little bit technical. You substitute it in here, but in the end you enforce the yield function, and from that obtain your plastic multiplier. Again, problems are not over, because you also have to define a stiffness matrix. You still have to solve the system at the structural level, which means Newton-Raphson method, which means derive potential stiffness matrix. Now, there's something there, is that we have to start from this expression. Sometimes in the old literature, you see still the expression between the stress rate and the strain rate. That's wrong, because if you differentiate these, you again have to first differentiate this part times this, and then the other part times this thing, times this delta. And that gives an additional term. And this additional term is crucial for obtaining rapid convergence. So how does it work? So we want to arrive at something like this. Your stress is some tensor stiffness matrix. We want to arrive at something like this. Stress rate is something like strain rate. So we start at something like this, where here you can derive that this h is this. You then substitute this into here. You enforce consistency, means that your yield function keeps to be enforced. And then you do quite a bit of manipulation and arrive at this expression. Now, the important thing is that in elastoplastic computations you get mesh independence. Well, this is an example of calculations with elastoplasticity. In this case, I have used a plastic potential function which is different from the yield function, not even including softening, no large deformations, but already difference between having a different yield function from plastic potential is sufficient to lose elasticity, which means it's sufficient to get mesh dependence without even material softening. And then you get this. You see, for a coarse mesh, it's one element white. For a finer mesh, it's one element white. For an even finer mesh, it's one element white. And the finer you go, the finer become, the smaller become, thinner become your shear bands. Now, if you include the Costra effect, you get a different picture. Obviously, when your mesh is too coarse to resolve the shear band or the fracture zone or whatever, you still have some mesh dependence. But when you go finer, it becomes good. So obviously your mesh must always be fine enough, but when it is fine enough, it should converge to a finite width of your localization zone. In this case, a shear band. In the case of fracture, a zone of distributed fractures. And that was it for today.